So I want to talk about regression a little bit. I'm like doing this new stats class, and it's like opening my mind to why stats is cool. Like I've always known it's important, but I definitely can see truly how cool and powerful it is just from this basic course, man. This professor's the bomb. So regression. So the whole point about stats is the statistics is about analyzing the differences and the randomness between data, right? So let's just take some data and then talk about it. So let's say and I like to do the engineers versus literature students. So let's say we have a sample of engineering students, right? All right, so we got our sample of engineering students. Let's say we got 15 students. That's our sample, okay? And then let's say we have at the same time a sample of literature students, right? Let's say we take 15 lit students as well. This is our sample. So we have a bunch of engineering students and a bunch of lit students. So this is the sample size. They'll call that N in the textbook, sample size N, right? And we're looking at their IQs, right? And so we're looking at, and I'll put that in blue, I guess, as like purple as like a top marker. So we're trying to analyze the IQs of engineers versus, come on now, of engineers versus literature students, right? So we're trying to analyze that. What you could do when you're talking about regression takes two data sets and compares them. All right, so regression takes two data sets and compares them. It's a way of comparing them. I'm sorry, I shouldn't say it compares them. It does do that, but it's not the only way. So it takes two data sets and it compares them. The point of regression is to determine if the two variables are related to each other. Finds if two variables, and in this case, we're talking the IQ of the engineers versus the IQ of the literature students, right? We're trying to see if they are related, if two variables are related. Okay, obviously, the engineering students and the literature students aren't particularly related, right? But I just kind of threw up some information here because it doesn't matter if they are or not. So that's what the regression does. That's its like job. And so in a book, when you see related, it'll talk about like, are they? How would the book say it? It would be like, do they correspond to one another? I'm trying to think of different ways that it could be presented. That's too small. I'll put it in a different sense. Sometimes they'll be like, do they correspond, right? Or they'll ask you, is there or like, do they influence each other, right? Still, they'll have statements like that basically to talk about, does one affect the other? That's the whole idea. Okay, so that's what the regression analysis does. I guess, how do you do that? So the way to do it, I think I'll put that in blue. How? So basically what you're going to do is you're going to graph both data points. So graph data points. Okay, so let's say you graph them on as one with an X. And so in this case, I'll put the engineers as the X and I'll put the literature students as the Y. Now you can do this with anything, honestly. Yeah, I know engineers students and literature students don't have an actual correspondence. Maybe they do actually. I don't even know until I do the analysis. But a lot of time you do this for something that's a bit more applicable, like I don't know, like the effect of global warming on hurricanes. I actually looked into that. I found a really, really interesting response. But yeah, so you could look at like the amount of hurricanes as one axis versus the year as another axis, because we know global warming is supposed to get hotter every year. And so you could look at like the year and then the amount of hurricanes. You could put the year on one axis and the amount of hurricanes on the other axis. The whole idea is you're going to graph your data points. And so in our case, we're going to put this axis and this axis. So this is our engineers and this is our lit. And then let's say, I don't know, boom, 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 boom. And we'll say we have a dot here. So when one engineering student has that, we'll just compare them 1 to 1. So we'll go the first engineering student we found with the first lit student that we found. So we'll go 1, and then go 2, 3, 4, 5, 6, 7, 8, 9, 10, right? 11, 12, 13, 14, 15. So we'll get this displacement, right? And so we compare all the students and we get all of these dots. And so once you've gotten all these dots, you want to see the trend between them. You can look at it and start to see the trend, right? So you can look at it and tell that I've designed this so that they are roughly a positive trend. So what you're going to do from here So first you graph it. Second thing you do is you create a regression line. Regression line. Okay, and all the regression line is the trend. All right, it's going to come in the form y equals mx plus b. Okay, where m is your slope and b is your y-intercept. Okay, so what that'll look like on here roughly is something that's like that. And that's going to have some equation, right? And that's going to be your regression line, blah, 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 blah. That's what it'll look like, okay? And from the regression line, you can tell some information, like the slope will tell you about how these guys are compared. The smaller the slope, the less positive the trend, you know. So slope is going to tell you about positive trend versus negative trend versus almost no trend. The y-intercept, most of the time, I'm not going to lie to you, the y-intercept is kind of useless. It's not to say that it's always useless. It's just to say that a lot of time it doesn't really apply. Like in this case, the y-intercept is talking about the case where there are 0 engineering students versus how many lit students. But you can see, based on my graph, that's saying if I have 0 engineering students, then my lit students will still have an IQ. So if my engineering student was non-existent, I would have a lit student that had an IQ, even though, you know, I don't have anybody to compare it to. And so that kind of doesn't really make sense. And so that actually happens oftentimes with the y-intercept, but that's not the point here. So you do your regression line after you've graphed your points. Once you've done your regression line, then you're going to calculate r squared. Okay, you can calculate r or r squared. We tend to go with r squared. So calculate r and r squared. Okay, if you have a Excel, it's literally as easy as just kind of getting the Excel to do it. If you have to do it by hand, sorry fam. You calculate r and r squared. These basically give a sense of the randomness, okay? These give a sense of the randomness of the data about the line. And so basically what I'm saying is if I look at my data set and I average the distance from each of my points to my line, you see how they're all a different distance? That distance represents the randomness of the data from the idea that I was trying to go with on calculating the line equation. So the line equation is an estimate, but the actual data is different from that, and they differ by that factor of randomness, r versus r squared. Typically, we use the r squared, okay? That's the one that I use, the r squared. And so the more randomness you have, shoot, I'm saying it backward. The bigger the r squared, the better the fit. I'm sorry, I got that backward. It is a measure of the randomness, but the bigger the r, the better your situation is, because r goes toward from 0 to 1. So we have r and r squared, and they move from 0 to 1. From 0 to 1, and the closer to 1, the better. And so this is going to be a better fit. Better fit. Okay. So basically what they're trying to say is as you move toward 1, that randomness is going to cap out. So basically what I'm saying is this guy and this guy and this guy and this guy, because they're all very close to the line, they're they better fit the equation, and so we can predict them a little bit better. Okay. So that's r squared. Once you find your r squared, then you can do you basically find your p-value from there. And so last but not least, you find your p-value. Find p-value. Okay. And so all of this I'm actually saying with the understanding that you can use like an Excel package to do this. And so I'm not talking about the equations that do it. All right. So you find your p-value. If your p-value is bigger than 0.05, then you can say that they're not strongly correlated. Okay. So I got bigger than and smaller than. So if your p-value is bigger than 5%, they're not strongly correlated. Okay. If your p-value is smaller than 0.05, then they are strongly correlated, which means that they are influencing each other. Are strong correlation. Okay. And so this is just a little bit of theory that I've kind of like ran into as I was doing this class. I thought it was interesting, something I just wanted to kind of like put out there. Not really talking about the math, just talking about the ideas, because a lot of time if you don't have the idea right, then you can't really get to the part where you're doing the math. And so hopefully this helps some people. If I have any fixes, then I'll fix it. I'll just add to this as I keep learning. But all in all, I hope this helped.